So I said this. This class is intended to prepare people that make, measure, and model materials to work in the field of quantum information science. It's the kind of setting the stage, setting the platform so that you can get more advanced training. Okay, so we're going to start at the very beginning because that's a very good place to start, as they say. All right, so when we think about quantum information science and engineering, it really encompasses a lot of different areas, including computing, sensing, communication, cryptography. And at the heart of all of those technologies is the thing we call the qubit, or quantum bit. And to understand what a qubit is, it really helps to come back to what a bit is. So what's a bit? Yeah, so it's a binary digit. Typically, we think of it as 0 or 1, true or false, on or off, plus or minus. And it is a representation of the logical state, and the correspondence between those values, 0 and 1, and the physical state of the underlying system is dependent on how the computer is programmed. So that's kind of up to the programmer to say what the 0 and 1 represent. And so we can draw an analogy or contrast between this classical bit, which stores information in a computer, and a simple light switch. So the light is either on or off. Forget the dimming lights. It's not dependent on me being in the room to observe it. So 0 or 1. The light is on or off. All right, so what about this quantum bit? So that's the qubit. So let's consider the light switch again. A quantum light switch could be represented by a sphere like I have drawn on the right here, with the north pole being off and the south pole being on. And imagine I'm going to put this special light switch in a room that's separate from the light, and I'm going to control the switch by putting my finger somewhere on the sphere. So I'm in the room with the light switch, and the light is in a different room. If I put my finger on the north pole, the light will definitely be off. And if I put my finger on the south pole, the light is definitely on. You can go to the room and check. That's always going to be the case. But if I move my finger anywhere else on this sphere, the light might be on or off. And when you check, you'll know whether it's on or off. If you don't check, the light is in some indeterminate state. It's not dimmed. It just exists with some probability of being on or off when seen. So if I put my finger here, I'm in an indeterminate state. So some probability. As soon as I walk into the room and I check, the light is on or off. The act of me going into the room and checking it out forced it to be that way. And this quantum light switch that we've created is an example of a two-state quantum system. All right, so a quantum bit, the qubit that we're going to be talking about, is another example of a two-state quantum system. And it's the basic information unit in quantum computing. So with the qubit, we're going to replace our on and off on our quantum light switch that we just created with two states that we call 0 and 1. The north pole is usually referred to as 0, and the south pole is usually referred to as 1. And these kets that I've drawn just represent those quantum states. And the important point about a qubit versus a classical bit is that it can be in a state other than 0 or 1. It's possible to form linear combinations of those states, and we call those superpositions. So the state of my qubit is equal to some coefficient alpha times 0 plus some coefficient beta times 1. So we're here. This is the state of my qubit. So we cannot examine a qubit to determine its quantum state. We can't determine alpha and beta. Instead, quantum mechanics tells us that we can only learn something that's kind of more restricted about this qubit. When we measure it, we get either 0 with a probability alpha squared, or we get 1 with probability beta squared. And there's a normalization sort of requirement. The probabilities have to sum to 1, so we do know that alpha squared plus beta squared is equal to 1. So this kind of dichotomy between the unobservable state of the qubit and the observations that we make is really at the heart of quantum mechanics and quantum computation and quantum information. It makes it hard to intuit the behavior of this quantum system, but there's an indirect correspondence between the qubit states, and we can indirect correspondence between the qubit states, and they can be manipulated and transformed in ways that lead to measurement outcomes that depend on the different properties of those states. So a single qubit by itself, not so interesting, because it is, when you observe it, either going to be on or off. But when it starts interacting with other qubits, the state that it was in before it was measured is going to influence what happens with the other qubits. And it's the whole system that allows you to kind of get more out of it than what you observe when you observe it. Yeah, so the systems, these quantum systems, have real experimentally observable consequences. All right, so because we have this normalization, alpha squared plus beta squared equals 1, we can define our quantum state in terms of polar coordinates, or we can use this 3D sphere, so we can go back to our spherical light switch. And so I have sort of the polar coordinates defined here relative to Cartesian axes. And so we have some angle theta, which is measured away from the z-axis, and we have some angle phi, which is away from the x-axis. And so if I rewrite my quantum state in terms of polar coordinates, it would look something like this. So we have our quantum state equals cosine theta over 2 times 0 plus e to the I phi sine theta over 2 times 1. So this thing is called the block sphere, and as we're going to see, it gives us kind of a physical place to go back to when we get confused about what our qubits are doing or telling us, or where how they're being manipulated. I find it to be a very useful tool, and I think you will as well. So we know that classical bits store only 2 values, 0 and 1. And we can combine them in large units to store greater ranges of values. And the question is, how much information can a qubit store? So the whole sphere is kind of my qubit, right? There's technically an infinite number of points on this unit sphere, right? So in principle, I could sort of store the entirety of Shakespeare in this one qubit. But that's kind of misleading because this single qubit will give either 0 or 1 when I measure it. So from a single measurement of a qubit, we only get a single bit of information about the state of the qubit. This was sort of what I was trying to say, but maybe a little bit more, less elegantly before. But how much information is represented by a qubit if we don't measure it? That's kind of the question. Well, it's kind of a trick question, because how much information can be represented by a qubit if we don't measure it? 0. I mean, you eventually have to measure it to learn something about it. But there's something really important in that trick question, because when nature evolves a closed quantum system of qubits, she keeps track of all the continuous variables that describe each individual state, like A and B or theta and phi. And so there's all this hidden information. And what we'll see is that this hidden information grows exponentially with the number of qubits. So instead of having a binary system with our typical logic bits, in qubit land, we have this system that grows exponentially. So for every qubit, we should be able to take on the values of 2 to the n bits. So if we have n qubits, we should be able to take on the values of 2 to the n bits. Because let's think about 2 bits, 0 and 1. I can have 0, 0, I can have 0, 1, I can have 1, 0, or 1, 1. And 2 qubits could take on all of those values at once. So 1 qubit can take on the value of 2 bits, 2 qubits can take on a value of 4 bits, and in general, n qubits can take on the value of 2 to the n bits. All right, so if you start looking at tables like this, which kind of show like numbers of qubits versus like compute time, so this particular table is assuming times based on a classical computer with a clock speed of 3 gigahertz. So that's 3 billion operations per second. So that's kind of a typical computer, classical computer. So if I have 1,000 qubits, that can store the same number, the same amount of information as 10 to the 301 bits. 10 to the 301, that's a wild number. So let me think. That's like 3 universes worth of hydrogen atoms. It's a humongous number. And the amount of time that it would have taken a classical computer to do that calculation is 10 to the 284 years. So the age of our universe is like 13.5 billion years old. So this is much, 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 much longer than that. So 1,000 qubits isn't even the end of what could be possible. If you kind of look at state-of-the-art quantum computers that have been built by people like Google and IBM, they have reports of systems with 50 and 75 qubits operating together, maybe not without faults and errors. They're not quite to 1,000 yet, but it's early days, right? And so we could imagine getting to systems with some of the platforms we'll talk about that could get us to several thousand, maybe tens of thousands of qubits in a single device. And yeah, the amount of computing power you could have at your fingertips with that is pretty astronomical. All right, so what? What are people going to do with all of this computing power? The thing that I think is really awesome is that when you go to like a computer science talk on the prospects of quantum information, they always use chemistry as their example of why this is going to change the world, which I think is really cool. So they always give the example of like nitrogenase. So nitrogenase is a very complex protein that fixes dinitrogen and makes ammonia. And we have an industrial process that does that same thing. We don't really understand how either system works. But if we had a quantum computer that could precisely describe this complex protein, we would have a chance of understanding it. That's kind of the logic. It's somewhat faulty logic, as we'll walk through with this example. So what molecule is this? Does anybody recognize it? It's one you all love. Yeah, it is caffeine. All right, so caffeine. So caffeine has 24 atoms. So it's pretty small molecule in the grand scheme of things. Let's go back to thinking about our orders of magnitude. An 8-ounce cup of coffee has something like 95 milligrams of caffeine, and that's about 3 times 10 to the 20th molecules of caffeine. And what we're asking to model here is not all of the molecules in a cup of coffee. It's just this one 24-atom molecule. So why is this hard? It's hard because these 24 atoms can exist in 10 to the 48th distinct quantum states. So if we want to perfectly describe it, we need the ability to represent all of these different atomic states or configurations. So this 10 to the 48th comes from the number of positions that our electrons can occupy in the ground state of this molecule. So, for example, in our hydrogen atoms, we have a 1s orbital that can hold 2 electrons. So, yeah, there are 2 kind of quantum states that we need to consider. And in the minimal basis set that we want to consider representing this as, we're going to have 1 qubit for each quantum state. So, or 1 bit for each quantum state. So that's 10 to the 48 bits. And the question is, how many qubits would we need to hold the same amount of information? So if we kind of go to our 2 to the n logic, 2 to the 160 is 1.46 times 10 to the 48. So that would be good. That would allow us to hold everything about what this, all of the electronic states, quantum states of this molecule. Now, what's annoying to me as a chemist about this kind of analysis, okay, so what we're saying is that we could perfectly describe the ground state of caffeine with a quantum computer that had 160 qubits. Yeah, okay, but is that useful? Not really. I mean, what we want to be able to do is understand more than just the ground state. We want to understand reactions. We want to do something useful. And we don't even, like, it's sort of more complicated than that because we need to somehow program this computer to hold that information, which is not trivial at all. So it is for sure more complicated than that. All right. And so the thing I want to leave you with today is that beyond sort of the prospects, or I guess because of the prospects for the amount of additional computing power that a quantum computer could get us, this field has really turned into big business opportunity. And I think that is why there's been all of this emphasis from funding agencies and leadership of countries to push scientists towards quantum information. So this is a report that came out this past year, or earlier this year, from McKinsey. And they estimate that the potential quantum technology market by 2040 is going to be $106 billion. And of that, about, well, it's a big range, $9 to $93 billion is going to be in quantum computing, and then smaller amounts in quantum communication and quantum sensing, which we'll talk about next week. The potential economic value from quantum computing, based on the investments that are going to be made, are estimated to be like really large. You know, thousands of billions of dollars of investment. So far, the United States government has invested about $34 billion, and that has translated into sort of what is seen at the bottom row there. So there's 50 quantum master's degree programs around the country. There's 180 universities with quantum research groups. There's, verging on 2,000 quantum-related patents granted just in 2022. And there's, 44,000 publications on this topic. And so this was sort of part of the impetus for creating a class like this, is to make sure that we don't miss the boat. So if we look at sort of the current market map for quantum computing or quantum information in general, you can see that it's a very complex landscape. So we have just a snapshot of who might use this technology eventually. And there's people like Bank of America or Merck on there. And then you have sort of the companies that are developing software and other pieces that are going to be essential to making quantum computing useful. And then you have the people actually developing the quantum computing platforms. And then you have people building things that are going to be necessary for putting a quantum computer together. So these ones in the middle we'll talk a little bit more about. The ones on the side are pretty interesting from a chemist and material scientist perspective, I think, and maybe we can talk some more about them tomorrow. But things like cryogens end up being really, really important because most quantum computers are operating at liquid helium temperatures or lower. Different light sources and lasers, lots of other components. And so when we dig in and we look at companies, startup companies mostly, that have grown up around actually building quantum computers, they've all kind of put a stamp on a different qubit platform. So you can see the different platforms that you all will learn about over the course of your project. So there's superconducting qubits, whole range of companies that have kind of said, we believe this is going to be the path forward. So D-Wave, for example, IBM Quantum, Rigetti, Amazon. There's ion trap quantum computers. IonQ, for example, has said, we believe this is the way. Neutral atoms, people like QISE and Quanta. Silicon-based qubits, qubit technology, so Intel, no surprise, says silicon is the way. And as y'all will see when you dig into the silicon qubit area, they basically tried to just shift everything and all the infrastructure that they've built up around making silicon-based electronics to this problem. And then there's photonic quantum computing. So companies like Xanadu and PsiQuantum are trying to do quantum computing with light. So these are all real things that are happening. The landscape, as you'll see when you read the article from Soto for Friday, is fluctuating. So some people's funding has been pulled, and others people have gotten more funding, and so you can kind of get a sense for where you think the field is going to, go in terms of which qubit platform might win. But it's still at such early days that research on all of them is absolutely critical.